How are you doing?
Recording is on.
Okay, we can start then. Good afternoon, everyone. Welcome to today's session of this webinar series organized by the Young International Committee on Predictive Modeling in Foods. yICPMF is a global initiative of early career scientists working to promote education, collaboration, and knowledge sharing in the field of predictive microbiology and food modeling. This free open access webinar series is part of our mission to build a strong international community by connecting students, researchers, and professionals with experts in the field. We're really happy that you're joining us today, whether you're here live or watching the recording later. We also have a few housekeeping rules to ensure that the session will run smoothly. So first of all, today's session is going to be recorded, as you all saw, and both the video and presentation slides will be shared with all the registered participants in the end. Please keep also your microphone muted during the talk, and if you have any questions, you can type them anytime in the Q&A document or in the chat box. We'll collect them and present them to the speaker during the session or in the Q&A at the end. Please also make sure to stay with us until the end of the lecture and the Q&A. At the end, we will ask you to fill in the attendance form, which is required in order for you to receive your certificate. We will also be taking a group picture, as we normally do, for our LinkedIn post after the Q&A, so we kindly invite you to turn on your cameras at the time, of course, if you're comfortable to do so. Feel also free to engage and network with us via our Slack community and follow us on LinkedIn for more updates on upcoming webinars. Finally, if you have any technical issues, please message one of the hosts directly in the chat and we will try to help you as fast and as quick as possible. So that was with the housekeeping rules that we have. I think that now I can introduce the speaker of today. So it's our pleasure to welcome Professor Dr. Alberto Garre. Alberto Garre holds a PhD from the Polytechnic University of Cartagena, where he received the award for the best doctoral thesis in food microbiology in 2018. He has also been awarded several postdoctoral contracts like Fundación Seneca, MSCA, Maria Zambrano, Ramón y Cajal, and recognitions such as the Best Young Scientist in Food Microbiology Award in 2024. His scientific contributions include methodological advances in predictive microbiology, machine learning and Bayesian statistics, participation in 14 projects, authorship of more than 70 peer-reviewed articles, and leadership as principal investigator in 6 projects. He also holds editorial and guest editor positions in leading journals. His social impact is reflected in 9 technology transfer contracts, regulatory contributions in ISO and other committees, and work as an external expert for ISAN and EFSA. Moreover, he's involved in outreach activities through IDIS program or Cartagena PNSA initiatives, while also supervising and mentoring PhD theses, 3 completed and 2 ongoing, more than 20 master's and undergraduate theses, but also Euphoria Fellows. So I think this was a good and small introduction on Alberto's activities. And now I believe it's time to give the floor to Alberto, who will present the bioinactivation and biogrowth software used for robust modeling of inactivation and growth under isothermal and dynamic conditions. Please, Alberto, the floor is yours.
Yes, thank you. Thank you very much, Hara, for the kind introduction. So you can hear me, see my screen and everything, right?
Yes, that's correct.
Yeah, I see people nodding. Yeah, well, so yeah, it's a great pleasure for me to be here because the goal of this talk is to explain a bit what bioinactivation, especially in a bit of biogrowth, so what they are, why we implemented them, and why where we are going with them. So, and at the end of the day, they are software applications for the community, and the quality of a software application is not based on how complicated or how complex it is, but the values find it. So for me, having the possibility to communicate it and to disseminate it and to have feedback from potential people who might be interested in using it. So for me, it's always very very valuable to guide further development. So then to tell you a bit about, well, I'm coming from the University of Cartagena. We are a port city in the southeast corner of Spain, so that means we have good weather. We're at 20 Celsius more or less today. We have nice food, so a pretty nice place to live. And then, so we are a polytechnic university, and I'm within the agro-food, agro-food school. And then within this school, I'm in the food safety and preservation unit. And here we do different things related to biotechnology and food safety. And let me arrange stuff. Yeah, okay. So then the thing is that many people don't know is that before doing the PhD, so I'm a mechanical engineer by training, and yes, so then I spent 3 years working for the aircraft industry, doing some types of different stress calculations, and I didn't like the that career, and I wanted to have a change of path. So then I started doing a PhD in food microbiology, and I don't have a picture of my first days in the laboratory, but it was something similar to this. So just imagine that I had done mechanical engineering, so I had never taken a lecture in biology, food safety, food science. So everything was very new to me. So they took me into the lab, and it was very clear for everyone that my my work was not going to be successful as I continued in the lab. So I had to find something different to do. But the situation was that I looked at my colleagues and the same face that I had when I had to deal with the laboratory equipment. So when they had to analyze data, build models, all this kind of stuff, so they had a similar expression. So then that's why during the beginning of my PhD, so that's why we started developing bioinactivation. And the main goal was to make life easier for my lab mates, the other people who were working in the same laboratory as I, because they had to do all type of things in predictive microbiology, so fitting models, making predictions under dynamic conditions, doing model validation, all this kind of stuff that were quite complex for them to do. So then I try to make their life easier. So then that's why we developed first the bioinactivation package. And well, so you have it here. It's been in CRAN for quite some time, and we have been updating it regularly. So then in this paper you have the description. So it's almost almost 10 years old. But what it does is to make life easier. So then so if you want to fit a dynamic model, so if you have tried to do it from scratch, then that takes quite some time. But then if you do it with just 26 lines of code, so then you can get the upload, you can fit the model, get a plot showing how good it compares to the data, and then all the statistical information of the fit. And I was happy because then for me that before I had to do it from scratch, but then I saw it to my colleagues, and then they still had the same expression, because at the end of the day, an R package requires to some R coding, so you need to be able to code, and that was not their case. So that's why using this Shiny package for R, so then we develop a web application. So then the advantage of using Shiny is that we can have a user-friendly web application that can run any R package or any combination of R packages in the background. So the advantage of this was that we should obtain the same results. So then if we fit a model using this web application or the R package, because they are at the end of the day using the same functions, so it should provide the same results. And well, so it has been evolving for quite some time. So this is the paper where we describe the web application. It's from 2018. So the thing is that because we have been updating and changing some things in the application through the year based on the kind of needs that people had. So the paper has been it's quite outdated. So then if you want to really know why we did it, so it's good that you take a look. But if you just want to use it, it's better to use either the manuals that are included in the application or this package over here. So what can bioinactivation do? So it has functions for making predictions and functions for fitting models. And then when it comes to making predictions, so you can make them just from primary models. combining primary and secondary models to describe dynamic conditions, considering parameter uncertainty, so Monte Carlo simulations and all this kind of stuff. And then when it comes to model fitting, so you can fit primary models, or you can fit primary and secondary models in 2 steps or 1 step. And then you can also fit models directly from dynamic data. So the idea of this presentation is to guide you a bit about the different typical scenarios where we can use bioinactivation. And yes, I have data from previous projects and this kind of stuff. So I believe there are 5, well, maybe 6 main applications of the software. So the first one is for teaching, and that it's for that I use the isothermal predictions. Then the second one is that we want to know if something impacts the inactivation kinetics. So we want to see if some antimicrobial has a synergistic effect with thermal inactivation or not. So then we will use primary fitting, or we want to see if there are differences between different strains of Listeria. So then we will use the primary fitting. Then when we want to characterize and be able to summarize the response of the microorganism to thermal inactivation, so then we would use one-step fitting or two-step fitting, but one-step fitting is always is going to be always more robust. And then if we want to design or to validate or verify some type of industrial treatment or pasteurization or sterilization treatment, then we will use dynamic predictions. And then if we want to describe the kinetics in a way that should be more effective from the point of view of the more informative, from the point of view of the amount of data that we need, so then we can do dynamic fitting. So then through this presentation, we will go through through each one of these different case studies. So the first one, the teaching. I don't know if you, because you are the young ICPMF, so some of you are already involved in teaching or not. So then the first time when I presented bioinactivation in a conference, somebody told me, yeah, this can be very useful for teaching. I dismissed that comment at all because I was not teaching. I thought that this was way too serious thing for use it for something so silly as teaching. But then I started teaching myself, and then I had to teach a bunch of 20-somethings what is a primary model, what is a secondary model, what is a d-value, what is a tail, what is a solder, what is a nonlinearity. And often when I do that, then I would start writing equations in the blackboard, and usually this represents quite well how the response is. But then nowadays, well, I didn't show you the link. Well, so you have it in the slides, but then I opened the one for growth. Yes, so Bioinactivation, so it's a web application, it's open access, is available, everything you want. So yes, and you just type this and then you can access it. You had it in one of the slides. They will be shared. So yeah, I'm running it locally because sometimes the internet can give me some issues, and that's why here there are some numbers instead of the address. But yeah, it's the same thing. So so this is Bioinactivation as you open it. So then as you can see, it's arranged in different modules. So then here on the left-hand side, you can browse between the different modules. So then you have some modules for making predictions and some for model fitting, and then also some documentation and some about pages. So if we go for the ones for making predictions, so this is the one that I use a lot when I'm teaching, and let me make this a bit bigger. Yeah. Yeah, so this is the one that I use a lot when I'm teaching, because if I want to teach what the Bigelow model is, so instead of writing the equation and start drawing the whiteboard, I say, okay, so then this is the Bigelow model, and then if we have a d-value of 2, so then Bigelow d of 2 minutes, and then I click on making prediction, and then here you can see what the prediction is going to be. And then I say, if I want to explain what the t-value is, so then I change this number over here and then make the prediction again. And then I can already show what the difference is, that if you have a lower t-value, then you're going to have a faster inactivation, that then this parameter is going to describe how long you need to to make the to have one log reduction, and then if I want to show the numbers here, so time for one log reduction. So sorry, how much did I put? 8. Yeah, so time for one log reduction, so from 8 to 7. So if we have a d value of 2 minutes, it's 2, and if we have a d value of 1 minute, it is 1. And then if I want to show a nonlinearity, so then I show that there are different primary models, and then if we want to have a Weibull model, so then this would be a Weibull model where p is equal to 1, and then I can show that this is equivalent to the Bigelow model, because then when we have a p of 1 is the same, but then if we have a 1 of 0.7, we have one curvature in one direction. That should be this one over here. And then if we have a p that is higher than 1, so then we have the other direction. So then besides teaching, you can use, yeah, I think that in most applications, we don't just use primary models for describing thermal inactivation, because we need also the secondary models. But then this already provides, for teaching, it's very, it's very useful. Yeah, so then besides teaching, we can use it for other things that are starting to be more relevant for PhD students and research. And a typical scenario is that I have one colleague that wants to study the effect of something on thermal inactivation. And for instance, this was the case of Leonidas, who was doing his PhD here in Cartagena. And then what he did is that he had some Bacillus cereus strain, and then he wanted to see if some pre-adaptation of 48 Celsius before the application of the thermal treatment. So, and if that was going to impact in any way the inactivation kinetics of the microorganism. And then what he did is, this is a Martia thermocystometer. That is a device that we patented 15 years ago. So not we, but my laboratory, my department. And yeah, so then we had some experiments where we just had the Bacillus subtilis culture and others that were pre-adapted. So then we applied some different isothermal treatments, and then we had these plates. So then this is Leo looking at his data, and this is how it looked like. So then he had experiments at 50, 51, 52.5, and 55 Celsius. And then he had experiments with the mutant strain, the wild type strain, and then whether there was a pre-adaptation or not. And the classical way of analyzing this would be to just take one time point or 2 time points, and then doing some, for instance, you can do some 2K, ANOVA, all this kind of thing to see if there are differences. But then in that case, so imagine that if you take the time point over here, so then you would see that there was a big difference. But then if you take it afterwards, so at this point, they all tend to converge. So if you really want to understand the kinetics, so then predictive microbiology is really, really going to help you a lot. So then just to show you, I have the raw data. This is Leo. So this is how Leo's data look like. And well, I only have the 52.5, but then he had experiments under for the 3 different types of microbial culture. So if you go to bioinactivation, so you go here to the left, we want to fit models, and we want to fit right now primary models, because we are only looking at 52.5 Celsius. So then first you need to upload the data, because it cannot know it. So then you can upload it as an Excel file, a text file, or manually. It's easier to upload it manually, because this is basically like a fake Excel that we plugged into here. So you can just select something and write numbers, and you can insert rows, remove rows, all this kind of stuff. But what you can also do is that you can copy paste. So then this is the wild type strain. And then if you copy and paste, then you see that you have all the data. So you load it, and then you take a look to be sure that there was no problem when I uploaded the data. So then this was the type of data that Leo had. So yeah, so then first, then what we need to do is select what model we are going to try to fit. So then we have all sorts of primary models over here. So as starters, we can start with the Bigelow model. And then because this uses nonlinear regression, so we need initial guess, but then as long as they are reasonable, you convert to the same model. If you are way too way too far away, yeah, okay, I cannot break it. But then what you can see already here, smaller size. Yeah, so then you can see that the model, the data has a curvature that the model itself does not have because it's a Bigelow model. So then that's why we should try a different model, for instance, Mafar model. And then you see that this one looks way better. Then if you're happy with this model, you can go down here and then you can see the parameter estimates of the model. So you have for the delta value, the estimate and standard error, for the curvature parameters, same thing, for the initial concentration, parameter correlations, and then also the standard error of the residuals. Yeah, so then in this case, because of reasons, we use this different type of model that consider that there is some two slopes, so then that there is a transition time and then an initial d-value and a second d-value. And then so that's why we have these three model parameters over here. So yeah, so then Leo did it for all his four conditions. There's no point in doing it here because I have the results. So then what he did is that then for the wild type so then this is at 52.5 and 55 Celsius for the wild type, the SIGP mutant, then under control conditions. So then these two dots, dots over here. And then when we had the pre-adaptation. So what were we seeing here? That in all the situations where when we did not have the pre-adaptation, so we had these non-linearities where we had two lines, whereas in the case where we had the pre-adaptation, so the orange one, there is only one bar over there because then in all cases was linear. And then also it was interesting that in all the cases of the t-value that we had in the after the pre-adaptation, so then it was similar to the t-value that we had in this second phase of the control conditions. So yeah, so then we did some interpretation that then the first part of the thermal inactivation was there was some dynamic acclimation that was similar to the one that we had during a pre-adaptation. And yeah, so then that's something that we would not have been able to conclude if we only looked at time point and we use 2K or more classical methods. But yeah, so it's a long story and we have some hypotheses for it. So if you want to see how we do it, then go into the paper. So we have used this kind of approach in many different studies. So then if we want to see the effect of different, well, this was a similar study. Harry is also a co-author here, but then it was a similar study on Salmonella. Then we applied it for hydrostatic pressure, if there was a synergistic effect with liquid limonene and thermal and heat treatment. What was the role of SIGP should be capital, for Listeria monocytogenes. So these kind of methodologies of doing experiments under isothermal conditions, fitting primary models and trying to conclude something from there. So and that's it's very useful and it can really help you to analyze, to understand better the microbial response. So the third case study is when we have some colleague that was asked by someone to summarize, to characterize what is the thermal inactivation of a microorganism. And then for that, they need to use a model. So then they have basically two questions. What model equations should I use? And what model parameters should I assign to those equations? Because if we have straight line, we have an intercept and a slope, and if we have something nonlinear, so we have more. But then we are always going to have some model parameters. And then here I always have people telling me one of my least favorite quotes that is that all models are wrong, but some are useful. And this was said by Vox quite some time ago, but then he was talking about parsimony, and then there it made a lot of sense. But then people tend to use it as an excuse for using bad models, and I don't see it like that. So because this fact that all models are wrong, so it's rather a reason for quantifying and reporting the error, and also a motivation for developing methods that are able to reduce that error. So then first we need to think why are models wrong, and the reason for that is our experiments, and not it's not the fault of experiments but of the modelers, because we are not able to build models from basic principles. So then we need to really go to the lab and obtain data that is going to that we are going to use to build those models. So why are model grounds? So for two reasons. So then the equations are going to be simplifications. So then we are going to look at how the microbial concentration changes through time, so how some parameters are affected by temperature or any other factor. And then we are going to propose some equations that simplify that relationship. And then also because there are some errors in parameter estimation, because once we have this equation, so in this case we have this T1, this T2, this T so then we have three parameters that we need to estimate from that data. And yeah, and then it's very obvious that all the experimental observations that we have that we obtain have some amount of error, not just people messing up the experiments, but all the limitations of the techniques. And then if we use observations with error to estimate some parameters, so then it makes sense that also those parameters must have some error. And that's why, because this is very obvious, that I get upset when I see these kind of things in publications. So the one on the left is from 20 years ago, so they have an excuse, but this one is for this year. So it's relatively common to see it's very small, but yes, so it's relatively common to see some scientific articles where they report some parameter estimates and they just an estimate without any kind of uncertainty estimation. So standard deviation, standard error, confidence interval. So these estimates are unreliable and things should not be published like this. So yeah, so if you review papers and then you see this type of tables, so major revision. It should be, they need to report something. So yeah, so then what is the interpretation of this parameter uncertainty? So one way to see it is, okay, so if we repeated the experiment using the same experimental design, the same people, the same equipment, everything, so would we get the same values of the parameter estimates? So there are two ways to obtain this, and we can either fit a model. So let's say, for instance, Leo, so he did this experiment with the pre-adaptation at 52.5 Celsius 3 times, so that he would have three replicates. So one thing we could do is to take each one of the replicates, fit a primary model, so that would give us three instances of the d-value, and then report the mean and standard deviation of those three d-values. Or another thing that we could do is to fit a single model and report the error of regression. So just to show it to you here, so it would be this error over here, okay? And yes, so we did that. Well, it was for growth models, but the conclusions are the same. So we did in this paper over here, some numerical analysis. And then what we saw is that the error of regression is more robust than doing this thing of fitting a model for each one of the replicates. There's a good reason for that, and it's explained over here. So, but the message is that you should use the error of regression. So second approach. And the way that you should the interpretation that you should follow for this uncertainty is that whenever you have a parameter estimate and a standard error, so if you repeated the experiment, so the distribution of this parameter estimate could follow a normal distribution with the mean given by this thing, so 1.3 over here, and then the standard deviation, so the sigma given by this 0.15. Okay. So another thing that you can think about when thinking about our parameter uncertainty, or model uncertainty, so it's whether a model is good enough. and then not just if the model parameters, the parameter estimates that you are obtaining, whether they are how much trust we have in them, but also how much dispersion we have around the model predictions. So there are mainly three indices that are used. So the root mean square error, the standard error of the residuals, or the accuracy factor. All of them are based on the residuals. So the difference between the fitted value and the fitted curve and the observation. So this straight line, this vertical line over here, and yeah, so it's an algebraic relationship of them. So we haven't done it for, because the typical question that I have from PhD students is that they have a model fit and they say, is it good enough or not? So we did a systematic literature review for growth models, and then what we concluded was that the standard error of the residuals is more stable, so it's the one that should be used. And it's possible to define benchmark values, but they are going to depend a lot on how you do the model fitting, the experimental protocol, and the type of media. So this is under review, and then we have some numbers for growth. For inactivation, we haven't done it because I think it depends a lot on the type of experimental method, because here we use this Mastia thermocystometer, and then it gives us a precision. If we are using thermal bath, so then it's very different. So I don't think it's really comparable. So then what we use in our lab is that the standard error of the residual should be between 0.15, 0.4, more or less. So it depends a lot. If we have a laboratory media that is very homogeneous, so we are closer to 0.2. If we have a food product like a smoothie or kale, so then we are higher. And yeah, because it's harder to do the experiment. But yeah, but then for that you should know your equipment and your laboratory and define your own benchmarks and your own thresholds. But still, regardless of all these indices, so it's always recommended to follow good practices, so that for all conditions, so you should have at least 6 time points. For all the conditions, if you're going to fit a model, so have at least 2 log reductions in the microbial concentration, because if we have an error of 0.5 and we have 1 log reduction, so we don't know if we are observing the reduction or the error. And yeah, also if you're going to build secondary models, so have a broad coverage and always use technical and biological replicates. So things that seem obvious and basic, but sometimes people forget. So how can we reduce this error of the models? So there are two approaches: experimental design or fitting methods. So the experimental design, so gathering more data points, or if you go more to the laboratory and you have more information to fit the model, so you should have also better models. And then you can also use optimal or better designs. And yes, so we have published a few for microbial inactivation, so you can take a look. The problem with those is that uh, they are not trivial to calculate, and yeah, and also in many cases you need a lot of information to define them. So then what I think is more interesting in many cases is what fitting method you use, because yeah, so you can do the fitting of any predictive microbiology model in either 2 steps or in 1 step. 2 steps. So you fit the primary model for each one of the conditions that we have, and I have an example in case you haven't done that before. But then what we get is for each one of those conditions. So at 52 Celsius, AD value; at 55 Celsius, another D value. So we have a table of parameters, and then we fit secondary models to that table. The alternative is to use this one-step approach, when we fit both the primary and the secondary models at the same time. So there is not an intermediate step. So we did again for microbial growth, but then it should be the same for inactivation. That is the conclusion. And then the relevant thing here is that if you compare between the green and the blue, so this is how much uncertainty we have if we use the 2 steps, of how much dispersion we have, and this is how much we have for if we use the 1 step. So it's relevant because they use exactly the same amount of data. So you are not going to the laboratory to get more data, but you are getting better models by using a more robust fitting algorithm. So yeah, so after all this complaining, how do we do all this stuff in, in bioinactivation? So yeah, so then if you go here to the part of model fitting, so you have both the two steps and the one step approach. And okay, I have yeah, Gerardo. Yeah, so Gerardo was the one who wanted to do experiments, and then so he went to the lab, and it was on listeria on coconut water. So then he did experiment at 50 Celsius, 52.5, 55, 57, and 60, and then he looked at how the microbial concentration changed through time. So then again, you first need to upload the data, and this. Yeah, and then you can upload it as using our fake Excel here. So you copy, paste, and if you load, you can see here how the data looks like. So see, so there are different temperatures and different changes in the microbial concentration. If you go down, just select what primary model you want to fit, and then so by some magic, so you are going to get. So for each one of the conditions of the experiments that Leo had, no, Gerardo, sorry. So then we have a different primary model fitted. So then that gives us, so for each one of these temperatures, say a D value. And if we just say, yeah, 55. So then we can fit the secondary model and get here both the parameter estimates and the standard error of the t value at the reference temperature. So this temperature over here, and also the set value. So you can know that if we change this thing over here, so the fitted curve is exactly the same. And then also the set value, the difference is this thing over here. It's because the reference temperature in this context, at least, so it's something that we use to facilitate the interpretation of the model, because we need a slope and an intercept, and then it's at what temperature we are referring this intercept. So then as the alternative, because I've been complaining, well, you can also use, for instance, a variable type model and the same thing. So then you see that you fit a primary model for all the conditions. And then here is when you already start seeing that the two steps is not the best, because besides getting a delta value for all the temperatures, then you also get a curvature parameter for each one of the temperatures. And that's not advisable, because what I have seen from studies in the literature, so when they say that there is an effect of temperature on these curvature parameters, so they don't have very, very strong evidence. And it's generally advisable that we keep this parameter constant. So yeah, so then besides this, so then the recommended approach is to use the one-step one, and it uses pretty much, Gerardo, I need to close Leo because I'm messing up. Yes, so Gerardo, so this was the data for the one step. So for the two steps, for the one step, we use the same type of data, but note that instead of using the microbial concentration over here, so then we use the number of log reductions. And there is a technical reason for that, but again, copy, we load it using our fake Excel over here. We load it, and then you see that now instead of starting on 5, 6 logs, so we are starting at 0 log because we have log reductions. And again, we go here. This is nonlinear regression, so we need some initial guesses, and then say that we get. So now instead of getting one primary model for each one of the conditions of the software or the nonlinear regression magic, what it's doing is that it's estimating, so based on all the data, the set value and the d value that are the ones that better describe the data. And yeah, and then if you want to use a different model, for instance, a FAR model, so
Alberto, sorry to interrupt you. There is a message popping up saying that your screen is turned off to save bandwidth. I don't know
what? Sorry, it's what?
Your screen turns black a bit, and it says that it's turned off to save bandwidth. Sometimes. I don't know if it's happening to everyone, but yeah.
Yeah, I cannot change the bandwidth.
It does happen. Yeah, it does happen quite often. Yes.
Yeah.
Maybe try to turn off the camera, maybe. I don't know.
Yeah, maybe I can try and turn off my camera. Give me a second. Okay, yeah, my face is not important. Yes, so aquí estamos. Okay, so yeah, so we were fitting the Bigelow model and it looked like this. So then if you choose the MapFar model, this, yeah, I put. Yeah, so then you see that then now we are fitting the MAFAR model and now realize that before when we were using the two steps for MAFAR, so then the curvature was adapting to the data in all the cases. So then we have downwards or upwards depending on the temperature. But now because we force in the one step to have a unique p-value, so then for curvature parameter, so this one over here, so then you see that the curvature is always the same for all the curves. So yeah, so then this is the overall the recommended approach for so yeah. So the way I would recommend that you go to model fitting is do not just ditch two steps because the thing is that it's always a nice way to see. So because you have to look at the primary model, so then you can decide if you want a nonlinear or a linear model, and then you can also verify that the secondary model follows describes the microbial kinetics. Because if you just follow the one-step approach, so you will get some global fits over here, some parameter estimates over here, but then, for instance, it's not easy to see if the secondary model is describing the microbial kinetics. So I would always advise you to go first here, fit the primary and secondary models using the two-step, select based on that, what model you're going to use, what type of model equations, and then you go to the one steps, fit the model like the final fit, and yeah, and then this is the numbers that you report. And also report standard errors because otherwise I'm going to be very upset with you. And yes, so how else? Another case study. So the another situation that is that okay. So now we have already summarized what is the inactivation kinetics of the microorganism, and then we have fake company that wants to validate a given treatment. So they have designed their time temperature profile, and they want to validate that is going to have these 6 log reductions. And then the problem for that is that everything, well, not everything, but most of the information that we obtain in the laboratory is isothermal because we have our Mastia thermostometer. We put the whatever medium we are going to use, we set it at 60 Celsius, and then once it's stable at 60 Celsius, then we inoculate a bit of the 10 milliliters of the inoculum. But companies don't do that because then the ingredients are going to be at room temperature or refrigeration temperature, depending on the food, and then the pasteurization is going to take place at least at 60 Celsius. And thermodynamics does not allow for temperatures to go suddenly in an instant from those 20 to 60 Celsius. So instead of having a sudden, an instantaneous heating, so we are going to have this type of thing. And yeah, and then in this case of things, so it's not clear to them how they should calculate what is the number of log reductions that they have, and yeah, so then why we have this data from this project. Yeah. So yeah, so then what we do is that we go to the company, we take we put some probe over there, and then we see through time, so how the temperature is changing. So then what we can do with that is go to if you go to Bioinactivation, go to dynamic predictions, and then here uploading the data using this. We can use the just for the just for the sake of it, so you see how it works. How do I call it? Rep. Yes, so you browse, temperatures, you select the set where you have the data, you load it, And here you see what is the data that we have. And yeah, and then we could go here, and then because we had already characterized the thermal inactivation, so the deep value goes around 1, more or less. Don't remember, doesn't matter too much. And yeah, so then what are these would be the parameters that we have. It's not cheat. Yes, so then we would take the same model parameters that we have then here. So then we would plug them here because it's what summarizes how the thermal inactivation of that microorganism. So then here we would say the treatment time, and then the application could make, in many cases it looks very ugly, but it's because the y limits of the y-axis are not correct. So we can see the temperature, and then so for this temperature profiles, then this could be the expected microthermal inactivation kinetics. And then from this we can see, so for instance, when we would reach these 6 log reductions, for instance, so then it could be at this point over here. So yeah, so then for this, what we can do is that if we go to the company, we see for different operations, so then we can see how close they are to this limit. And then so this could be the theoretical part, but then quite often we also go and somehow we manage to take some using a surrogate in many cases, and then we can see the changes in microbial concentration during an actual treatment. And then so what we can do is that also here within this dynamic prediction, we go to compare against data, upload the data, and this is how the data look, and this is how this prediction compares against the data. And then we see that it's pretty much well aligned. So then we can trust this prediction. Yeah, so then this could be about verifying thermal treatment. So then another type of thing that we can do with bioinactivation, that something that can help you with, is that we want to do this characterization of the thermal inactivation kinetics, but then instead of using a bunch of isothermal treatments, so then we want to use just one dynamic temperature profile. So it could be that instead of having several treatments of isothermal conditions, then we want to use these dynamic conditions. So then this is what Gerardo did during his PhD, and then he would obtain this kind of data. So then this orange line would be the temperature, so it would go from 30 to 70, and then he would see how the microbial concentration changes through time. So why go through all the trouble of getting this dynamic data? Because the reason why we do isothermal treatments is because we need to, if we want to build a secondary model, and then we want to describe the effect of temperature changes between 55 and 60 Celsius on the thermal inactivation of Listeria. So then if we use isothermal treatment, so then we would need to do independent treatment of 55, 57, 58, 60, whatever. But the thing is that if we use a dynamic experiment, so then because we are doing the heating from 30 to 60, so we are somehow observing what is the microbial response through that so through the whole range. And in principle, they can be more informative than using these parallel isothermal treatments. So we have it also depends a lot on the kind of experimental design that you use. So here we have some analysis, then also Eva Balsa from Vigo we have all the references to her studies over there. But then you can get more informative data. So instead of having all this much uncertainty, so then you can have this lead. So how could we do it? So then what Gerardo this one. Yes, the dynamic treatment. So then the type of data that Gerardo would obtain is that for different types of thermal treatments or profiles, so it would have, so then see that the temperature is changing. So he starts at 35 and then he reaches 65, and then there are different profiles. So then this is over 10 minutes, this one is over 45 minutes. So yeah. So then you need to, so how can you do this in bioinactivation? So then, because we want to fit a model under dynamic conditions, so first you need to upload your temperature conditions. So then you use your file Excel, copy this, you check that then this is how the temperature changes through time in your experiment, and you upload your microbial data like this, like the changes in log n, you load it, just check that it looks reasonable. And then now is the complicated part because then you need to define initial guesses for the model parameters because nonlinear regression is a bit complicated for that. And well, so you have a bunch of different models that you can use. But so then for each one of the model parameters, you need to define it. And then to help you a bit, so you here on the left-hand side, so you see what could be the black one is the model prediction according to the initial guess. So then could be so then you can see how the black line changes, and the blue and purple ones are for the upper and the lower bound. And yes, so then this you should do it carefully because otherwise the algorithm may not converge, and dynamic inactivation, especially if you use nonlinear models, is not the most stable. But then because I have already prepared this example, so I know it works. So then here what the software shows you is this. So then you can show the temperature. So what is this? So the thing is that this is of all the possible values that the value and the set value can take. So then these ones over here are the ones that better describe this data. And then because we have the value at a reference temperature and a set value, so then we have both the secondary model and also the primary model because they are both coupled. And again, so you have the parameter correlation over here, standard error of the residuals, and then you want to have some residual analysis over there. And yeah, so that's pretty much the main. I think that those are the main case studies of how this thing can help people. And yes, so what is next? So one thing that we will be implementing on the R package is the one-step fitting of the Garre model. Because the thing is that if you want to fit a model in one step, you need secondary models for all the model parameters. And the issue is that the shoulder length of Garre was not so well defined because the relationship between the d-value and temperature is log linear. Pretty much everybody pretty much agrees on that. For the Garre model, the effect on temperature or on the shoulder length was not so agreed on. And yes, so then we did some analysis, rather theoretical here, and then we read something that makes sense. So then that will be implemented here. And I'm also working on an update of the package because it's almost 10 years old. So then there are some things that can be improved. So then if you want to take a look, it works. This second version of Bioinactivation, and it's not fully documented. So, but if you are curious on what we are doing, then you can take a look. And then for the web application, so mainly make it prettier. So then right now we are working mostly on the R package. So just wanted to mention, because I have it in the title of the presentation, BioGrowth. So it's pretty much the same thing that we did for inactivation, but then because it's for growth, so instead of being bioinactivation, it's bio. So it's also an R package and a web application. So it's arranged in the same way, different modules here that you can do either isothermal, dynamic, or prediction with uncertainty, Monte Carlo simulations, and also fit in different types of primary model, dynamic, and you have even more stuff here. So I think it's better because I did it almost 7 years later, so I knew how to code better. So yeah, but then basically it's the same philosophy. So then you can can do model fitting. Well, this is from the R package. So yeah, you get all the statistical summaries, the visualizations. You can try different primary models like Barangay or Gompers. You can also do model comparison based on yICPMF and then also visualization and model parameters. You can do also all these same things for dynamic conditions, but then you can define gamma type model, so then it's more flexible. And then you can also do global fitting, and when rather than a simple dynamic experiment, you fit several ones in parallel. And yes, so then you can also do predictions based on primary models or under dynamic conditions, and then you can also do this kind of thing with parameter uncertainty. And yes, so it's also the link is the same, but instead of growth inactivation, growth. So this, so you know that it exists. And yes, so then to close up a bit, so then the one thing that we have been always very careful with when developing growth in bioinactivation is about transparency. Because the thing is that if we want to help people understand their data, people care a lot about their data. And then if we believe that if we want them to trust us with their data and the conclusions of the analysis, so we should be very transparent with all the methods. So and that's why everything that we have in bioinactivation and biogrowth is open code. So you can access it from many different places. So it's closed, but then if you go here to the documentation, so then you have a user manual over here that is very detailed, and then it has how many pages? 30, many pages. But then you see that there are many screenshots of, okay, so if you want to make a prediction, first click here, then here, and it's very there. And then you also have, so in GitHub, that's the second one, because I open it more often. And yeah, but then you have for the R package, so you can go here and check for all the functions and all the code. So then you can go here and check if I made a mistake somewhere. Also, for the web application. So if you want to see how I was struggling with signing, so then you can also go here and see everything. So yeah, so then just to keep it transparent. So if there is something that looks odd, so then you can go there, check it. And yeah, and if you see something, just send me an email or open a pull request if you know how to deal with Git or open an issue. You can do all these kind of things there. And yes, so then just to close up, so bioinactivation started as a way to help my colleagues in Cartagena. Biogrowth was also a way to help my colleagues, but then more in Wageningen. And yes, I think they are quite mature now, and they have reached a point where they can not just help my colleagues from my laboratory, but the overall predictive microbiology community. And yeah, and then as said, so and that's why I'm always very glad when I get this type of invitation, because the development should be guided by the feedback that I get from the community. And yes, so many of the functions of some small changes were based on colleagues asking me to change something or add something. And then when it's simple and it can really help, then I do it as fast as I can. The problem is that I don't have much time for coding nowadays. And yeah, then in this sense, I think that if we want to build this trust relationship between the software tools and the people who are using it, so transparency, that means open code, so it's key. And yes, so thank you, gracias. In case someone is interested, we have this call here in Cartagena. So it's similar to a Marie Curie program, but instead of being the postdoc people applying for it, is that the university, or the department, the school applied, and then they got package of 16 postdoctoral positions. So it's with the same conditions as the Marie Curie, but then instead of you applying to the commission and getting graded, so then the department already got the the grants for this type of project, and then so you would apply for this. So this should be less competitive than a conventional Marie Curie postdoc. So yes, and you have the link here for the call with the different topics that there are, and there are a few. So this because there are 8 that open now, and the other 8 will open in 1 year, I think. And yes, so then this, for instance, this topic could fit quite well within what you, I guess, the interest of this topic. And yeah, so as said, so I always appreciate any kind of feedback. So yeah, you have my email over here, and then if you want to discuss or make some suggestion to see something that doesn't make sense or that is wrong, so you can always email me. And yeah, so as said, thank you. And I think we have time for a few questions right now, right?
Thanks, Alberto. We do have some time for the questions. I have a few questions collected from the participants. And the first question is, how do you avoid overfitting when using more complex inactivation model with several parameters?
Okay, mainly. So then what I would do is first explore the data to see. So for instance, using a two-step. So if you have isothermal data, so a bunch of different isothermal experiments, so use first a two-step approach to see if there is need for more complex models. And if it's clear from that, because in many cases you see that the primary model is linear except for one replicate, that you have a couple points that are going wrong. So then in those cases, maybe it's not too reasonable to use a nonlinear model in that case. And then if you have questions, so a Kaike is the go-to. So then you feed different model structures, and then you use a Kaike to select the best ones.
Thank you. So when using different model, when different model fits the data closely or similarly, what final criteria help you to choose one model over the others?
Yeah, okay. Yeah, because at the end of the day, it's going to balance parsimony and overall dispersion. So yeah, it's not because for biogrowth it's implemented in the package and it gives you, but now you can obtain it from the residuals and you don't need to calculate it. But yeah, okay.
Perfect. One very easy question regarding the use of this bioactivation tool. How much information or biological understanding is required to understand or use this inactivation tool?
It depends. Uh, yeah, well, at the end of the day, it's going to depend a lot on the kind of application that you want to use. So, for instance, when we do projects for companies, so we had a company that was doing some stew made out of beans, and then they wanted to make sure that they were causing 9 or 12 log reductions of the main microorganisms, of the main pathogens. So they didn't know what their main pathogens were. They had a recipe for preparing these beans, and then they wanted to be sure that that they had this sign based on quality criteria, so that then it was safe, and it was, so from the point of view of the food safety, that it was okay. So in that case, they just needed to, so then in that case, they needed to know what type of model, so what the value and set value they needed, and then what was the prediction. And the details of why this microorganism, or what is exactly, or how the inactivation is taking place, so then that was not relevant at all for them. But however, if for research, we had a postdoc here who really liked molecular biology, and then she was working with delta SIGP mutants of listeria, and yeah, the different mutations, not just delta SIGP, but also other genes. So then in that case, so she was using the outcome of the bioinactivation of the primary models to understand how to decide what of these mutations was the most relevant. So at the end of the day, it's a tool you can use to summarize data that goes beyond just looking at 2K and the ABCs of the number of log reductions that you have. But and yeah, so then it depends on what application you want to use it for.
Perfect. I'll request all of the audience to submit or to fill the form, attendance form. So the last question to Alberto is, so normally in the industrial application, how do you define that the model is good enough for the decision making? Even if it's not the best possible model, but what are the criteria that we should say that, okay, this is good enough for with respect to food safety point of view?
Yeah. So for the companies,
Yeah.
so it depends a lot on how far you are with respect to the to the boundary, to the dangerous area. Because if we in this company, so we did the model fits, and even if we increase the model parameters, so then because the t-value is a normal distribution, so we took the 95 percentile, so the very worst case scenario, and then we were predicting 16 log reductions. Then we also did the verification where we went to the company. We did some inoculation using surrogates, and we cannot detect it at all after the treatment. So then, because in that case we had a very big safety margin, so then we didn't have to go that much. If I had calculated 6 logs and then in the validation, so then I would have asked them to, yeah, well, at the end of the day it's their decision, but then I could have tried to improve the model, get more data, understand better what is going on there, because so at the end of the day you can, so as my recommendation would be to, if it's on a food safety application, so really company-wise, go into a worst case, and if in the worst case you have a reasonable safety margin, you are okay. If not, try to get more data and better information to have a better, a narrower worst case and more accurate worst case.
And the last question, what should be done when a one-step fitting approach yields a more robust model and a lower RMSE, yet fail to capture the key parameters such as the shoulder or the log or the leg or the tail?
Yeah, so then the thing is that so you can do a one-step fitting approach for anything. So I use so that's why you could use the 2 steps approach so that's why I do not advise to go directly into the one-step fitting, because then it's possible that there are some of these, like a shoulder or anything, or some odd kinetics or odd secondary model that you do not realize are there. So then I would go first doing the 2 steps approach, and if you have a very odd response, so maybe it's not implemented in Bioinactivation yet, so then you can send me an email, and then if it's simple, I can do it for you. But then otherwise, you can do, at the end of the day, a one-step approach is an optimization of the standard error of the residual based on some model parameters. So then if you have some odd microbial response with shoulders or odd stuff, so implement it, be able to calculate it, and then once you have done it, calculate a KICE and compare it against the simpler model, a Maffart or a Bigelow model, to really have evidence to say that this more complex model that you are using is justified based on a KICE.
Perfect. Thank you, Alberto. Can I ask all of you guys, all of in the audience, to keep the cameras on so we can capture an image for LinkedIn?